This tutorial will demonstrate how to recreate the classic stretch reflex that's found in almost every introductory neurobiology textbook. We'll be building this simulation on top of a previous tutorial. Please open the limb stiffness project that's located at C, Program Files, AnimatLab, Tutorials, Examples, Limb Stiffness. Once it's open, select the Save Project As menu item and rename this project to be Stretch Reflex. The Limb Stiffness project showed you how to build a simple two-segment arm and how to use limb stiffness to maintain an equilibrium joint position against disturbances. It also discussed how to use equilibrium set points to move the arm to different locations. This simulation starts out with the arm at an initial position, and then at 20 seconds it moves the set point to extend the arm to a new position. At 40 seconds it moves the set point back to flex the arm into the original position. Let's begin by changing the stimulus that moves the arm to begin at 10 seconds and end at 30 seconds. Then change the name of the existing chart to be muscles. Next, we need to add stretch receptors to our arm. Stretch receptors are dynamic sensors that allow an organism to detect the length and velocity of change in the muscle. It can use this to compare predicted movements to what's actually happening, so it can detect errors. These sensors are dynamic in the sense that the nervous system can adjust them to cancel the predicted movements. Stretch receptors are fibers that are interspersed in with the normal muscle fiber. But since there are so few of them, they produce very little tension. This means that when the muscle's length changes, the overall length of the stretch receptor will change by the same amount. Two types of signals come from these receptors. Type 1A fiber signals send back information on the velocity of the muscle, and Type 2 signals send back information on the length of the muscle. Alpha motor neurons control the tension of the normal muscle fibers, while gamma motor neurons control the stretch receptors. The 1A signal feeds back from the stretch receptor to synapse directly onto the alpha motor neurons. The 1A signal is an error signal that helps regulate the muscle tension when unforeseen perturbations occur. The 1A signal also synapses onto a 1A inhibitory interneuron that inhibits the antagonistic muscle. Select the linear heel stretch receptor as the default body part type and add it to the humerus. Change its name to bicep stretch. Set its KSE spring constant to 1 kN per meter, KPE to 0.2 kN per meter, and damping coefficient to 120 newtons per meter. Next, add bicep, humerus, and ulna muscle attachments to string this muscle onto the arm. Then change the L width parameter to be 10 centimeters. Open the stimulus tension curve and set the amplitude to 1 kilonewton, steepness to 150, and upper output value to 1 kilonewton. Finally, set the 1A discharge constant to be 1000 spikes per second. This constant converts the length of the SE spring section of the muscle into a discharge rate. Now, copy and paste the stretch receptor. Name it tricep stretch. Add muscle attachments for tricep, humerus, and ulna. And then set its L width parameter to be 10 centimeters. Now let's add some charts to see the responses of our stretch receptors. Add two new charts and name them bicep stretch and tricep stretch. Add items to each to view the tension, length, type 1A, and type 2 responses of the receptors. Now run the simulation. Notice that the tension in the bicep stretch is 0 until the arm is extended, and the tension in the tricep stretch is very slight, around 0.15 newtons. When the arm is extended, it drops like a rock and leaves us with a floor effect on our 1A signal. This is where it can't go lower than around 33.4 spikes per second. This won't work for what we need to do. We need the 1A signal to be responsive to both increases and decreases in tension. This means it will need some base level of tension already developed in the receptor. Then, changes in either direction will move the 1A firing rate away from that base level. Let's do this by going back to the behavioral editor and adding 2 new stretch receptor nodes. Name them bicep and tricep stretch. And set their spindle IDs to be the appropriate receptor. Next, copy the motor neuron and membrane neuron for the bicep muscle and paste it twice. Change the names to be SB, SN, and ST, SN. And bicep stretch activate and tricep stretch activate. These will be our gamma motor neurons that will control the tension and thus the length of the segments of our stretch receptors. Connect the neurons to the stretch receptor and leave the default source data type as membrane voltage and use the default gain values. Add a tonic current stimulus to both of our gamma motor neurons. Call them bicep or tricep stretch stim. Set them to be always active and change the current to be 66 nanoamps. Now run the simulation again. Now our stretch receptors internally generate 30 newtons of tension. This causes the 1A firing rate to be around 65 spikes per second. When the muscle is stretched, this rate is increased, and when it's relaxed, the rate is decreased. Also, you should keep in mind that the stretch receptors reports 30 newtons of tension. However, as I mentioned earlier, stretch receptors are so few in the actual muscle that they usually generate very little tension. It's easier though if you can use the same parameters for your muscles that you do for your stretch receptors. That way, a stimulus will have a similar effect on either one. This keeps you from having to try and deal with two completely different scales for your muscles and stretch receptors. To allow you to do this, the stretch receptors have a flag that determines if the tension it develops should actually be applied to the joint, just like a muscle. By default, stretch receptors do not actually apply any of the tension they develop, so think of this as an internal signal, and it's really the type 1A and type 2 fiber signals that are really important outputs for the stretch receptor. Now notice that when the arm moves, the 1A firing rate changes in both the bicep and tricep stretch receptors. This firing rate is supposed to be our error signal. So what that means is that even though we're making a voluntary movement, it's being interpreted as a perturbation that needs to be resisted. We need to co-activate the gamma motor neurons to compensate for the movement we're trying to make. This will modulate the gamma motor neurons' firing rate to maintain a steady tension and thus leave the 1A firing rate unchanged. To accomplish this, we need to have data on what the movement should be. Let's get that data by creating a new line chart and adding data items for the bicep stretch receptor's length and velocity. Only add those two items and in that order. Make sure that you keep the auto-collect interval set to true. The data needs to be collected with the same time interval as the physics time step. We'll collect data between 5 and 40 seconds. This will encompass both of our movements. Rename the chart Bicep Prediction. Now rerun the simulation and let it go for over 40 seconds. Once you've done that, export the data from this chart into a file. Rename the file to be biceppredictiondata.txt. Exporting a chart saves out all of its collected data into a tab-separated text file. Now add a new inverse muscle dynamic stimulus to our bicep gamma motor neuron. Call it bicep stretch gamma. This stimulus loads in the predictive data that we just generated and uses this to calculate the active tension that needs to be applied during the movement to maintain the initial tension level. It then takes this active tension and uses that to calculate the membrane voltage stimulus that will be needed to generate that tension level. Finally, you specify a conductance value and base voltage, and it uses all of these values to generate a current and then injects it into the motor neuron. We'll use this to generate the gamma motor signal that will modulate the length of the stretch receptors to compensate for the movements of our arm. In the nervous system, other parts of the brain, like the cerebellum, are responsible for doing these inverse dynamics calculations. Those systems determine how the stretch receptors should move in order to compensate for voluntary movements. But that's a very complicated topic that's still not fully understood. This stimulus will allow us to cheat and simplify things greatly. Set the muscle length property to be our bicep stretch receptor. Then set the muscle length data property to our data file that we just generated. To use this stimulus, we still need to know what values to use for the base voltage and the conductance. For the conductance, we basically want the current from this stimulus to produce the exact same tension level that our 66 nanoamp stretch stimulus provides. Rerun the simulation and view the data of the bicep stretch chart to see what the tension level of the bicep is at 3 seconds. Copy this value and then go to the Calculate Stim property of the bicep stretch receptor. Paste the value in the tension text box and hit Calculate. This tells us the membrane voltage that will be required to generate this tension level. Now, we want this stimulus to generate a positive current, so this means if we leave our base voltage as a default of negative 100 millivolts, then the voltage change it will produce will be negative 61.5 minus negative 100, which equals 38.5 millivolts. Now use this voltage and the desired current of 66 nanoamps to calculate the conductance. We get 66 nanoamps divided by 38.5 millivolts, which equals 1.71 microsiemens. Use this as our conductance value. Then we need to set the bicep stretch stimulus to end at 5.001 seconds, or we'll be getting a double current. Run the simulation. At 5 seconds, the tension is just a little low, so let's adjust the conductance value to be 1.72 microsiemens and try it again. This time it's spot on. Also, notice that now as our arm moves, the tension in the stretch receptor remains constant, and more importantly, so does the 1A firing rate. Now, even though it moves, we get no error signal from the stretch receptors because our gamma motor neurons adjusted the stretch receptors to compensate for these predicted movements. If you look at the type 2 fibers though, you'll see that their signal did change. This makes sense because they provide information on the length of the muscle, and that did change. If we go back and disable our inverse dynamic stimulus and set the stretch stimulus to always active again, we can see that without the gamma activation, our 1A signal changes noticeably compared to when we do have gamma coactivation. We can see this more clearly if we manually set the scale on the axis. Set it to be between 60 and 70 spikes per second. Now, we need to do the same thing for our tricep muscle. Create a predictive chart for it and export its data. Then create a new inverse muscle dynamic stimulus for it. Call it Tricep Stretch Gamma. Set its muscle ID to be Tricep Stretch and use the exported data. Set its conductance to the same value we used before of 1.72 microsiemens. Now open the Tricep Stretch chart. And set the tricep stretch stimulus to end at 5.001 seconds. Run the simulation again. Now the gamma motor neurons can predict the movements of the tricep muscle to maintain a steady 1A firing rate. The next thing we need to do is to add the feedback loops. The type 1A fiber signals directly synapse onto the alpha motor neurons to help them adjust to errors during movement. Also, they have 1A inhibitory interneurons that connect to the antagonistic muscles. But to keep things simpler, we'll only be adding in the direct connections in this tutorial. Draw connections from the stretch receptor nodes to their alpha motor neurons. For this to work, we want the base 1A firing rate of 65 spikes per second to generate half of the current stimulus that maintains the limb stiffness. The bicep neuron has a stimulus of 80 nanoamps, so 40 nanoamps needs to come from the 1A fibers.
Dividing 40 nanoamps by 65.2 spikes per second gives a value of 0.614 nanoamps.
Use this as the slope in our adapter. Similarly, for the tricep, it has a stimulus of 66 nanoamps, so 33 nanoamps of that needs to come from the 1A fiber. Dividing 33 nanoamps by 65.5 spikes per second gives a value of 0.506 nanoamps. Then go back and set the stimuli for the alpha motor neurons to be half their current values. Then run the simulation. Our gamma activation still cancels the movement as it should to maintain steady 1A firing rates. Now let's add a perturbation during the movement. Think of this as if you were trying to extend your arm and someone pushed on it for just a second. This will cause an error signal to be generated because the motion of your arm no longer matches the predicted values. This will cause tensions to develop that will attempt to fight that perturbation and move your hand back onto the desired trajectory. Add a force stimulus to the ulna. Name it perturbation. Set its end time to 11.1 seconds and start time to 11 seconds. Then add a torque around the x-axis of 0.2. Then run the simulation. Whoa, what happened there? It turns out that this is a dramatic demonstration of what happens when your feedback gain values are too high. When an error signal occurred, it caused the tricep muscle to compensate and increase its force. But the gain was so high it produced too much force and overshot its mark. This, in turn, caused the bicep muscle to try and compensate, and it also overshot, causing an oscillation. So what is it in our system that controls the feedback gain? This is the slope of the adapters connecting the type 1A fiber signal to the current input into the alpha motor neurons. We started off by just quickly calculating a value that would produce the correct currents we needed. But it's obvious now that this produces gains that are way too large. Let's go back and assume a slope of 0.1 nanoamps for both of our muscles this time, and then use the equation of a line to solve for the intercept that we'll need. This will give us lines that will produce the correct current at the base firing rate of the 1A fibers, but with a much smaller slope. For our bicep muscle, we have an intercept of 33.48 nanoamps, and for our tricep muscle, we get an intercept of 26.45 nanoamps. Go back and use these values in our adapters. Now let's try the simulation again and see what happens. This time we get a much nicer result. This time our perturbation pushed up on the arm, and feedback signals produce forces to compensate for this without going into an oscillatory feedback loop. Now that we have the feedback system intact, what do you think would happen if we try and move the arm without properly coactivating the gamma motor neurons to compensate for that movement? Let's go ahead and give it a shot and find out. First, disable the perturbation stimulus and close these charts. Then open the muscle chart and run the simulation. View the data to see what the rotation value of the elbow joint is once it's moved. At 20 seconds, the rotation is negative 0.414 radians. Now disable the stimuli for our gamma motor neurons and set the stretch receptor stimuli to be always on. Run the simulation again. We can clearly see that the arm moves only a fraction of the amount that it did before. If we view the data from the chart, then this time at 20 seconds, the rotation of the elbow is only negative 0.146 radians. This is a significant decrease from the last time when we had the gamma motor activation. So what caused this? Let's close this chart and open up the charts for the stretch receptors and rerun the simulation again. This time we can see that when the arm attempts to move and the gamma motor neurons are not coactivated, the 1A fibers change their firing rates and essentially treat these movements as perturbations or errors that need to be corrected. So they generate forces to compensate for the errors that greatly retard the movement. What this means is that in order to perform voluntary movements, your brain needs to be able to send the correct gamma coactivation signals to your stretch receptors to compensate for those movements. If this doesn't happen, then it becomes very difficult to move your arm. This tutorial has demonstrated how to build a rather advanced simulation of the stretch reflex, and it's discussed some important topics in the field of movement and locomotion planning.